All right, so what we're going to do here is look at our graph of cosecant and also talk about some of the behaviors of the graph. So something we want to keep in mind is that cosecant is the reciprocal function for sine. So what we can do is use 1 over sine for this function, or think of it as if you have the value for sine, then you just switch the numerator and denominator. So if we're working with sine, that means if we're looking at our unit circle, we're focusing on these y coordinates. What we're going to do is flip them. Switch those numerators and denominators. All right, I'm going to use increments. Actually, I'm going to start at negative pi. Let's look across from negative to positive. So I'm going to use similar setup as tangent and cotangent. So doing jumps of pi over 4. And let's see. All right, negative to positive. What I'm going to do is set up my axes. I'm going to put y-axis in the middle and the x-axis in the middle as well. There's x and y. All right, so grabbing these coordinates. And if it helps, what we could do is we could just grab the values for sine. So at negative pi, that is 0. At negative 3 pi over 4, that's negative root 2 over 2. That's negative 1, negative root 2 over 2, 0, root 2 over 2, 1, root 2 over 2, 0. So if we have those, then what we're going to do, and with these whole numbers, what can help is thinking about how there's this kind of hidden 1 that's dividing each of those, which just helps us visualize numerator and denominator for switching. So for cosecant, we're going to switch. So instead of 0 divided by 1, it's going to be 1 divided by 0, which is undefined. Here, we're going to switch, and just to kind of help out with the exact value. So if you have, I'm just going to use the positive version. If you have 2 over root 2, rationalizing this, so rationalize the denominator, you'll have 2 root 2 over 2, which is just root 2. So if we wanted the exact value, this would be negative root 2. When we get to graphing, something we're going to use because it's hard to visualize where root 2 is landing, this is about equal to 1.4, just to help us graph there. At negative pi over 2, so I'll become 1 divided by negative 1, which is still just negative 1. Negative root 2 over 2 will become negative root 2 with that. Sorry if I didn't make that clear enough. What I did is I flipped where we had root 2 over 2. I did 2 over root 2, and I just wanted to show you the simplified form. 1 divided by 0. 2 divided by root 2, which is the same as root 2. 1 divided by 1. 2 over root 2, which is same as root 2. 1 divided by 0. Undefined. All right, so we're going to see here our asymptotes coming up with these functions. And where they're going to come up in terms of our unit circle is happening at intervals of pi. So at 0, our function's undefined for cosecant, and at pi. And then any sort of revolution going around those is going to make our function undefined. So we're going to have an asymptote at x equals 0. So we're going to have an asymptote at our y-axis. And then I'm going to put pi 4 units away. And then out here will be 2 pi. And then we can see our pi over 4 increments there. But what I'm going to have is an asymptote at pi. I'll also have one at 2 pi. And same for the negative side. We'll have these scale of pi over 4, but then asymptote at negative pi, asymptote at negative 2 pi. All right, so let's see what's happening here. Let's jump over to these positive values. So at pi over 4, we're graphing root 2, which is 1.4. So what I'm going to do is have 2 squares equal to a unit of 1. Same on the negative side. So if I wanted to, I'm here at pi over 4, I go 1, and then here would be 0.5, so I'm just going to go a little bit less. So this is about 1.4. At pi over 2, we're at positive 1, and at 3 pi over 4, we're at that 1.4 again. So the shape that's going to come up here, because we have these asymptotes, which we'll get infinitely close to on either side, and then it's going to come through, and it isn't exactly, but it's close to the shape of a parabola. So that means we're going to come from positive infinity, connect these with a smooth curve, and then go off to positive infinity, all in that little window there. To the left of the y-axis on the negative side, what you can see is at negative 3 pi over 4, we're at negative root 2, so that would be a negative 1.4 down there. At negative pi over 2, we're at negative 1, and negative pi over 4, negative 1.4. So what we'll see down there is coming from negative infinity, going through that point, going through that point. So what we're going to have here are these kind of intervals separated by these asymptotes, where we'll have this parabola-like shape above the x-axis and below the x-axis. And then it just flip-flops. So if we go to the right of pi, it would be negative. And then it would go positive, negative, since it is periodic, and it would just repeat over and over. And let's see over here, positive. Like this. All right, so for cosecant, some key features. Our asymptote is there at the y-axis. We start above, then we go below. When we start getting into transformations, I don't worry too much about these points. I really just look for where this is and then just go above, and then if this is below, just go below. So in terms of key values that we're going to be plotting, we'll have asymptotes and then this kind of vertex point here. All right, let's talk about domain, range, and symmetry. So domain, we're seeing this same scenario where we have these intervals where our function's undefined. So it's not really intervals, it's these locations, but the locations occur by interval. So x is defined by that x cannot equal, and for us it's going to be intervals of pi. So we can't have 1 pi, 0 pi, -1, +2, +100, any interval of pi. So what we're going to do is we can just have pi times k, where k is an integer. Now our range here gets a little more complicated. It isn't going to be all real numbers. What we can see is there's this window here where our function's undefined. Like 0, we are never crossing the x-axis here with cosecant of x. Once we get into transformations, then all sorts of things are possible. But for our function, what we're seeing is that we have from negative infinity, we go up to -1 and including -1. We're defined at -1, but then we'll skip over, and then starting at +1 and including +1, we can go off to positive infinity. So in interval notation, what this will look like is we'll be coming from negative infinity, go up to and including -1, so we use that square bracket, and combine that with the interval starting at +1, going off to positive infinity. So with our range, we just have to show there's this window between -1 and +1 for outputs where we are not seeing our cosecant function. Symmetry, what you can see is it doesn't work to just reflect across the y-axis, but if we reflect across the y-axis and then across the x-axis, then we start landing on our function. So this is symmetric about the origin, which means this is an odd function. And the period of the graph. So something we're going to talk about when we get to our graph transformations is what I can see is this distance between asymptotes is a distance of pi. However, that is not the period of our graph. With tangent and cotangent it was, because when we passed that asymptote, our graph was just repeating. But that's not the case here. While it has the same general shape, there is a difference between positive and then turning into negative outputs. However, what we could see is you go positive, then negative, and then we return to that positive behavior. So it takes kind of two of these sets of asymptotes to occur. So where the asymptotes are separated by a distance of pi, the period of the graph actually spans 2 pi. So for that, our period's returning back to 2 pi. So when we get to transformations and working with b, we're going to be using 2 pi over b. Whereas with tangent and cotangent, we use pi because that was the length of the period. Though with these, we'll use 2 pi. All right. Now, before we go to the graph of secant, sometimes we start getting all of these graphs and can get overwhelming, and we need these tips and tricks to remember what the shape is. And if you want to, it can be kind of fun. I know my scale of fun in math is probably different than yours. But if you want to pause the video and on top of this graph, draw the sine function. Just draw a sine on top and see what it does. I'm going to go through it, but it can just be kind of fun to put it together on your own first. All right, if we drew sine, so sine starts at the origin and it returns back to the x-axis, so one full period is a distance of 2 pi. Halfway in between those values, we cross that x-axis, and then we start by going to the top and then go down. So our sine function goes like this, and continuing it on goes like this. So if you know the general behavior of your sine function, it can really help you draw your cosecant function. Wherever we cross the x-axis with our sine function is an asymptote. Every one of those zeros turns into an asymptote for cosecant. And then from there, these minimum and maximum values become the vertices for these parabola-like shapes. So with that, if you can't remember where cosecant starts, and same with, we'll look at secant, and we'll see the same thing kind of happen with cosine. If you remember sine and cosine, that can get you started with these graphs. So I'll come back to that when we kind of talk about our transformations and how I often do that instead of kind of memorizing where these asymptotes are landing and all of those pieces. I just keep in mind sine and cosine, and that can help you form these graphs.